Good afternoon, everyone. Welcome to IME for 75. Today is April
765.
the 8th, and today we're going to introduce more about linear program. More about linear regression, because I just finished the linear part of the linear programming in IME 470. And in the very beginning, let me share you something about how interesting and how easy it's going to be if we simply want to apply the thing that we have already learned. Let me start from the very beginning. Okay, close that. First, let me stop the video and share my screen. Screen share, I'm going to share this one with you. Okay, so you can see it, right? Oh, no, this is not the thing that I want to share. What I want to share is this, MATLAB. Let me make my screen. Okay, now this one. The first thing I want to do is that I'm gonna do this. I'm gonna copy and paste. Okay. Let me directly copy and paste. I'm tired to write the code again. Okay, here we go. Here's something that I coded it before. I put it training data to be 100 on purpose. The reason is because I want. Hello, Mahbooba, are you there?
Yes.
Okay. The reason is because so this one set up the mu x and the mu y, okay, and this set up the sigma x and sigma y, and the x y being this way. So I'm gonna plot x is equal, and then I'm gonna plot. First, let me plot x, and now let me plot y, and then let me use example data or. Then copy and paste. So in this case, I want to visualize my data. I want to see very clear what does my data really look like. I don't want the data to be too terrible or too good. You know what I mean? Okay, so probably it's going to be very well because let's call it ABC. Okay, let's run ABC now. Yes, because I tested it before. See, so this data is not too bad, also not too good. You know what I mean? Because I don't want to see something like this way. For example, let me put it to, for example, make it to be 50-50. If that's the case, then it's gonna probably be bad. Oops, let me close. Okay, so this is gonna be bad. Why? Because this classification is too simple. You know what I mean? It's super easy. Hello, Said. That's super easy to directly get a classification. I want somewhat they're gonna be close together. You know what I mean? But I don't want it to be too close, because too close you can you can simply, okay, that's the reason why. You can simply not really make any differentiation. For example, this one is already very close. It's gonna be difficult to do the classification. I think I set up to be 20 before. So 20, that means that's a bit close, but not too bad. For example, something like this way, okay? So we're gonna, based on this one, let's run the classification models. Arap, I know you are using MATLAB. Have you used the classification learned it before, the toolbox? Really? You've never played it? How about the NeuroBox toolbox? I mean, the neural network toolbox, deep learning toolbox in MATLAB? No? I cannot hear you. Please unmute yourself. Hello, Arab? Hello? Yeah. Can you hear me?
Yeah, I can hear you.
Okay. You've never used the toolbox before? No matter deep learning or machine learning toolbox in MATLAB? Never?
Yeah, I use some toolbox, but not for classification.
Okay. Anyway, let's play it. I guarantee you in several minutes you're gonna learn it. Super simple. Please allow me to turn on my fan because it does need the parallel computing, so to make it fast. And my laptop, it's a Core i7, so I'm running a fan. So you may hear some fan noise. Please excuse me. After that, I'm gonna turn it off. Oh, seriously? Okay. Open. Let's add a new one. So that's gonna happen, and then it's gonna ask you which one you want.
Ewan, can you hear me?
Yes, yes, I can hear you. What's up?
May I ask, because I joined you a little late. May I ask what is happening here?
Okay. So in the very beginning of the class, I wanna, before continue the linear regression. Remember, I promised you guys before that I said I want to show you something, how to use whatever software to do the classification, and I said it is really simple, right? So I'm doing it right now. I'm showing you how simple it is, and I guarantee you every one of you just use several minutes, you're gonna you're gonna know it. It's really simple. Where's my ABC here? I realized that I forgot one thing. That is, I forgot to put the label to the training data. That's why I cannot make the classification. Give me 1 second. Let me close this one. And then I do need a data. So for example, like, let's make it this. If it is X, I make it to be +1. Okay. If it's Y, then I make it to be -1. Okay. So have a look at here. So my axes are red color. So all of these gonna be +1, and the blue color, all of them gonna be -1. Okay. So let's make this so that I have ones. How many do I have? I have n, 1 column, and let me see how to make it. Okay, make it an x, and then the next column is gonna be ones and one. Sorry, -1 and 1. And then let me see, make a y. Here we go. Let me generate it again. What happened? Error. What is wrong?
So I think you should have the bracket after y, not.
No. I forgot to put this because I forgot. Now that should be correct. Oh, did I put a 1? I said once, and my hand put 1. Interesting. Now it's correct. Okay. So that this is my training data, and you're gonna see an image to be input data. So the input data is gonna be this way. So all these are axes with label 1, and all y's with the label -1, right? And the visualization of the data is in this way. Okay, now I wanna use a toolbox to do the classification. So you're gonna go here, app, and go to classification learner. I've already opened it. My computer is not that fast, so I don't wanna, I mean, reopen it again. Let me see, where is my, here you go. Here's the classification learner here. And let me take out my annotate the toolbar so that you can see it more clear. Okay, now I'm gonna open a new session, and it's here. Input is gonna be input data, and my response gonna be, let me see. Column 1 is going to be the response. Okay, so that means column 1 is going to be y. Okay, so now see how simple it is. So you just let me make it very big here. You just click, and guys, you may feel excited because most of the things here you've already learned. See it? Decision tree I didn't include, indeed. Discriminant analysis, logistic, naive regression, naive Bayes, SVM, nearest neighbor. See it? Most of them you've already learned. That means what, guys? You can already operate. If you're interested in, if you're okay with writing code, something, you can do many things by yourself already. However, if you're lazy, fine, let's play it. For example, let's play linear discriminant regression, linear discriminant, okay, and then train, okay, then who knows how much time. It doesn't even use a parallel tool, really? And done? Why? What happened? Why so fast at this time? Because before I played it, it's pretty slow. Okay, I don't know how many seconds, and the accuracy is 95.5. Pretty good. And you can see a circle means correct, and the cross means incorrect, and it made some mistakes here. These are some mistakes, and all others are correct. And the accuracy is 95.5. That's really good. Okay. So now you wanna say, okay, great. So, but how to make the prediction, right? It's meaningless. You just play it for on the what, on the training data. Okay. Oh, by the way, one thing I want to say is that first of all, total misclassification is 9. Total, how many data do you have? You have 200. So this is relatively good. Here, PCA disabled. I didn't use the PCA. PCA is something, because here I have only 2 dimensions. PCA is something, for example, suppose I have 200 dimensions, I'm gonna make the dimension reduction. Make it to be, for example, okay, for example, 3 dimensions, that's PCA. Here, because total I just have 2 dimensions, I'm not gonna do it. And then later, when we introduce PCA, I'm gonna enable PCA, let you see the magic here. Anyway, so to really make the model, you need to export the model. So it's here. Let me make all the thing to this monitor. So it's what is the name? Train model. What's this method? LDA, right? LDA. Okay, let's name it to be train model LDA. Now you go to your MATLAB. You're gonna see like this way. Y fit equal to blah blah blah. That means if you wanna have a Y fit, so just put a command like this way. It's gonna make the prediction for you. Let's play something to see whether it's really good or not. So the data is in this way, right? Let's do this. For example, suppose I want to play the prediction. Let me what number you like? How about 30-30, which is here. So if everything's correct, it should be give me a green color, right? Blue color, and the blue color should be, I forgot, blue color is which one? It's -1. So in my expectation, it should give me a -1 class. Let's see whether it's correct or not. 30, 30. Okay, -1. See it? How about we play something else? Let's say -30, -30. It should give you a +1. +1. See it? So in using this way, you can put whatever the Y fit there, whatever the X there, and then it's going to give you the prediction. Clear?
How about 40, -20?
I know your point. Sure, let's play. 40, -20.
Yes.
40, -20. Sure, let's play it. That's a
Should be
very good question.
-1.
Yeah, because I know what his point. His point is here. And be careful here. I didn't use the kernel. Okay, if I use the kernel, it's going to be more interesting. And you said a 40, -20, right? I'm curious
Yes.
to know it as well. Okay, and I predicted to be blue color.
Yeah, it's gonna be -1. Yeah.
Yeah.
What about 10 and 10?
Good question. Let's see. +1, which is red. Yeah, 10 should be red, isn't it?
Yes.
See, because more here. How about we play KNN? Okay, let's play KNN. You see how fast it is. That's why I said every one of you just use several minutes. You're gonna learn it. But is it really worth a PhD class? You know what I mean? Okay, let's just play. Let's say the fine KNN. Oh, okay. Let's play all KNN, whatever you want to play. No, sorry. No, I'm talking about all KNN. Where it is? All KNN. Okay, run. Oh my goodness, please. The good point is KNN is really fast. Great. The course KNN is really good here, which gives me 97%. And you can see by choosing different method, you can see, have a look, observe this part, see it? The results are pretty different. The misclassification number, for example, here I have 8 misclassification. Here I have 6 misclassification, see it? And you can also export the model. And this time, for example, I use the KNN. For example. And I click OK. And then I do what? I do this. Give me a number that you like. Give me a number that you like.
Um,
How about we play
20
10-10
and-
again? Because 10-10 is kind of difficult. 10-10 is something like here. But for KNN, it's very clear. 10-10 must be red. It must be +1.
But we tried it. It was +1.
No. I had to be careful. We tried it. Okay. Here I am using KNN. The core. Which KNN? Let's see. I forgot the course KNN or which KNN.
Oh, you changed the classifier?
The cosine. The cosine, not the course. The cosine KNN. To this is something like the. That's a good question. I don't know what is cosine KNN. That must be they define the distance. Maybe they use a cosine space. I'm not pretty sure what is the cosine KNN, but for sure the meaning is I define the metric, the distance metric, and then I use this metric to do the KNN. Okay, so now the thing is that. The thing is I use this one to predict the one, and I have a look at here. Yes, we did try 10-10, but at that case we tried LDA. You know what I mean? The models are different. Although, of course, I mean, the results are the same, because to be honest, this model is very simple. I give you only 100, 100, and I made the data specifically to be relatively close. Yes, I made it on purpose. However, you cannot say that it must be correct or must be always in this way. No, it's possible that in some situations, the model predictions could be very different. Okay. Hello.
Okay.
Oh, what happened? Why suddenly in my configuration I cannot see any of you? Let me see. Can you see me?
No,
Oh,
we
okay,
can
okay.
see you.
Yeah,
No.
okay, good. Just make sure that the connection is correct. Okay, so you in the same way you can train whatever model you like. Isn't it super simple? Let's say you can play, for example, SVM. Let's say SVM. Let's say SVM, but how to put a? I'm not sure. For SVM, how to put a, let's say, okay.
What kind of SVM is it? Is it soft margin?
No. Yes. SVM, it is always soft margin. Let's see. Let's play a Gaussian SVM in which the decision boundary is going to be Gaussian. Okay, let's play. Oh, you see it? It's better than the regular SVM. See it? 97.5. The bad point is that MATLAB, as far as I know, they don't plug the decision boundary for you. I wish they can plug the decision boundary. It's going to be very beautiful. Let me think about it. Give me some time. If I have time in the next lecture, I will try to show you a method to, or I can code it by myself, I can think, but it's going to take some time. So I'm going to kind of like simulate all the data, try to make a large area of the space, and then plot it, and then it's going to manually generate a decision boundary. That's the simplest and also maybe the stupidest method, but it must be working. I know it. So in this case, we can clearly see the decision boundary so that we can see, for example, for the Gaussian SVM, it's going to be very clear. You know what I mean? Of course, here I'm lazy, so I'm just using the app, the classification app of MATLAB. Otherwise, you can use the FitC SVM, and there you can choose different kernels. Okay, for example, here you can see kernel is Gaussian, kernel scale 1.4. See it? So 1.4, that means the gamma. You know what I mean? So this is super simple, isn't it? Just several minutes. Everybody over you will know it, right?
So I have a question here.
Yes.
Can we have the classifier in a graphical shape?
The classifier where? In where?
In the graphical representation. I mean, we can have in the plot that you have here, we have all the points.
Yes.
But what about the classifier? Can we see also it as a graphical representation? I mean,
here we go. Here, see it? It tells you that blue color is -1, orange color is +1. It showed you. What do you mean by classifier? You mean the method, right? The method.
No, I mean, for example, you know, in the class notes, in the examples that we have, the graphical representation in the examples, we have, for example, that hyperplane or that, you know, quadratic.
Okay, the boundary. You're talking about the boundary, right?
Yeah,
That's what I'm saying as well. That's the bad point of MATLAB classification. The toolbox, they do not provide it. What I just said was that I will try to code it, but it's gonna take some time. I'm not gonna show it on the class. I'm gonna play it, and then if it's done, I'm gonna directly show the result. So I'm gonna write a code so that, you know, as long as I know the method, the result, I'm gonna draw the manually generate the boundary, decision boundary. So in this case, it's gonna be very clear. You know what I mean? Okay. So in this case, for example, suppose I run the SVM with the kernel of Gaussian. For example, here it automatically set the Gaussian scale to be 1.4. Then you're gonna see something really beautiful. You know what I mean? Because here, for example, have a look here. This is linear SVM. See it? And this is what? This is kerneled Gaussian actually SVM. And it should be very different. You know what I mean? But here, I mean, it doesn't directly allow you to generate such a classification boundary. I wish I can, but I need some time to try to play it, you know, a little bit. But all these are, I mean, are not difficult, to be honest. You just need to spend a little time and you're gonna get it. These are, to be honest, far from, you know, this kind of models. This kind of things are gonna take you long time to learn, but these kind of things are super easy. Okay, get a point? Now you see the point, say why, for example, some people can learn cited, okay, not really cited, learn the machine learning in a short time, because that is the machine learning in their definition. You know what I mean? Which is very different from this machine learning. If this machine learning you can learn in several hours, you are a genius. I mean, all of this in several hours, you are a genius. That's it. Nobody can do it, I'm afraid. Okay, so no worry, everything is gonna worth it. Why? Because after doing all this, you're gonna know it very clear. For example, you can clearly see after about 2/3 of the semester, you have already known most of them. I don't have time to teach decision tree, to be unfortunately. Regarding different types of the, for example, cubic SVM, something, fine SVM, Gaussian, these are very simple. You just need to, for example, this is MATLAB, of course. You can just go to the MATLAB help. You're going to see the definition of them, or you can just simply search. As long as you know what is the quadratic, linear, quadratic, and some kernel SVM, all of these are very simple. You know what I mean? Also for the KNN, all of them are the same. Okay, regarding this kind of tree methods, I didn't. Boosted, I may discuss a little bit. And for today, one of the most famous algorithm in industry application is called the random boosted forest tree. How many of you have heard of it?
I have.
Who just said it? I cannot see the face because Mahbooba or Said?
Me, Mahbooba.
Okay. Can you let me see your face? Then you may ask me, why don't I show my video? The reason is because of this. My screen is this side. Okay, so I have two screens. This is my laptop screen, okay? And if I show my video, you're gonna see my head is always like this way. You know what I mean? Because that is my main screen. My laptop is small. I bought an external screen, so which is big. That's the reason why I turned off my video. It's not because I don't want to let you see me, because it's gonna be very weird. You know, my eyes gonna always be that direction. Okay, so okay, so the random the boosted random forest tree. Wait, I told you, right? I remember one day in your office I mentioned about this, and I told you about C45 as well, right?
Yes.
Anyway, maybe. But that method is the real, very applied industrial method. Nowadays, for example, doing this kind of advertisement recommendation in, let's say, YouTube or Facebook, all of them are using these algorithms. And trust me, all these algorithms, if you just want to learn, and if you just want to play something like this way, 2 hours, every one of you can learn it. That's too simple. The problem is that you cannot get a job by this. Because it's a PhD level, you know what I mean? So you need to learn the algorithms, and to show the convergence proof. It's not that easy. Okay, any questions about this? About how to play this? 30 minutes. I guess most of you have already, especially for Arab, because I know you are using MATLAB. For Said and Mahbooba, probably you don't use MATLAB, you're gonna use the Python. And the Python, no matter for OpenCV or TensorFlow, they have much stronger library and functions. So that all of this just the coding, very simple, but the principle is much more difficult and deeper and worth time for learning. Any questions for these kind of simple operations?
No.
No? Okay, very good. Regarding coding, I mean, I don't think I need to. Probably you are more familiar than me regarding the coding. Okay, very good. So let me close the MATLAB. Okay, now let's start our main part today, which is what? The linear regression. No. What is that? Linear regression, not linear programming. Yes, linear regression. Okay. It looks beautiful. Good. Lucky it's written by me, not directly open the book something. Okay. So in the last time, what we mentioned is the basic concept of linear regression, right? Okay. Now let's see. I stopped here. I remember I introduced the geometric interpretation of this square problem, right? Okay, this is very important. Trust me, you'd better understand it very well, because it's going to help you understanding many different other things. Okay, then we introduced a weighted problem, and this weighted problem actually has another understanding way. I'm going to introduce you here when I guess I haven't updated. I actually added one small section here with multiple outputs. We're going to mention it later. But today, the main part is the statistical inference. Okay. So can you see this part very clear? Or let me make it bigger. Maybe it's better.
Yes.
Let me see. I cannot. Can I make it a double screen? And I mean, 2-page scoring. And but if that case, can I still see the whole page? Okay, Control H works. Let me use this way. Okay, so here, let's have a look at the statistical inference. So by the statistical inference, what I mean is some properties of the model. So first of all, let's suppose the true model as this. True model, okay? But you don't know what is epsilon because epsilon is a normal distribution, 0 and sigma square. And you're gonna see we actually could have some very, very beautiful properties to estimate this sigma square. And I'm gonna show it later in the next page. And to make my life easier, I assume that suppose I have two observations, yi and yj, they don't have covariance. In other words, they're independent about this noise, okay? And also, I assume that it's a very, very, normal case, which means n is greater than or equal to p plus 1. And also, we have to assume, for example, this one exists. X is the full rank. All here we assume are normal. Everything's normal. Okay. Now, let's have a look at the property because finally, I still have to make it to be one page. Because display single page. Because what? Because here my beta is what? Let me write it down here. It's important. My beta equals to xt, x inverse of x t y. Okay. To make my life easier, okay, let me do it one time. That's going to be more clear, I think. All these are vectors or matrices so that they're going to be bold. Okay, my beta is this. So very clear. What's the distribution of your beta? Don't forget that here, your y is what? Your y equal to, oh, no BM, x beta, coding, thought. As this, okay? All of these, again, are vectors. So that you actually have what? If you plug this one inside, then you're gonna have, this gives you that your beta, what the hell, like that. Equals to this time this and this. Okay, then it's very clear. It must follow what? Normal distribution, right? Why? Because first of all, have a look at this part. This part, they cancel each other, so that this simply equals to beta plus this epsilon, right?
Yes.
So this is very clear normal distribution. Be careful here. This beta is a known beta, okay? Because this is a true model. This beta is my estimated OLS solution, okay? Least square solution. So, so you have this result, and this tells you very clear that it is normal distribution. So that.
So I have one question.
Yes.
Here. So beta hat equal beta plus projection in the error space. So
okay, give me a second. Let me write something here with mean Yes. Yes, Mahbuba.
Yes. So since error is following normal distribution, that's why you're saying it follows the beta hat follows normal distribution.
Yes, yes, because this is a constant.
Yes, yes, that's mean. Yeah.
Yeah, because this is a constant and this is also a constant. This
Yes.
is also a constant, right? Your epsilon is a normal distribution. Epsilon is 0, zero sigma square. So that the mean of this one must be beta. You know what I mean? You can simply do expectation, right? You can do expectation, for example, E. I don't know how to write this E here. Let me see. Do we have something grouped maybe? Oh, good. E of the beta. This equal to what? This equal to beta directly, right? Why? Because E of this one is 0. This is 0. And this is constant, so it's beta. Right? Okay, so in this case, I know it's a normal distribution. This one is beta. Then to see why the next one is correct. This is actually a very, very common conclusion that suppose, let's say, let me make my life easy. Let's say variance of x equal to, let's say, I should say, actually, let me use this column. I should use covariance, although it doesn't matter. Once you write a vector, everybody knows what I'm talking about. Suppose the covariance of your x is sigma. If your covariance of x is sigma, then what is the covariance of, let's say,
beta hat
of this? What I'm talking about this. Let's say, suppose I have a v. Okay, let me use an a. What this one should be? Any ideas?
Cov of ax.
At sigma. I forgot which one is t. Yeah, yes, a sigma at. That's gonna be. For example, this a. Suppose this a is a small a. As a scalar, you're gonna have a square, right? If this is not square, then you're gonna have atx at. To see why, have a definition. Check the definition. By definition, we have what? We have covariance of ax. This equal to what? Ax as a vector, okay? Equal to the expectation of. Oh no! I need to have. Okay. Let me maximize it. That's why some people really dislike this. It's gonna be very complicated here. I have to click because the left parenthesis, the right parenthesis, it doesn't work here. It equals to what? It equals to ax minus mu. Okay. Let me ask you, what is the mu of this? Suppose, let's say this, and expectation of, of x equal to mu. Okay. Now, first of all, do you agree with me that the expectation of ax equal to a mu? This is correct. Too simple, right?
Yes.
Okay. Now using this one, let's have a look at here. Ax, the mean is a mu, and this one times this t. Be careful again, especially Mahbuba. What is this?
Transpose.
Yeah, I know it's transpose, but what is this result? The result is what? Is it a vector? It's a matrix, okay? Again. A column vector times a row vector gives you a matrix, okay? Usually, if they're the same, for example, vector v times vector vt, it's called a rank 1 matrix. This operation is called a rank 1 operation. It has a lot of interesting things, especially like in spectrum theory. Okay, so then you're gonna have this way. If you have this way, you continue it, you're gonna see something very interesting. And then you're gonna have what? You're gonna have this. Take this A out. Take this A out. Now you know the point. Isn't it simple? These A's are constants, okay? A constant matrix. So this simply equals to what? Equals A times, okay, let me write it down again. This equal to this, okay? And this is what? This is nothing but A covariance of X and AT. Clear? That's how we get it. So this is A covariance of X and AT for any constant A and for any vector X. Okay. Now let's have a look at the problem. Our problem is what? Our problem is I have a beta, right? Beta equals to this. Okay. So now, oops. Go back to our problem. I have
you already found beta hat, so you can use it directly.
Yes. Thank you. Yes, yes. So I need to do it again. Covariance beta hat equal to covariance of this. Thank you, Said. That's really important. Right? And this directly equal to what? This directly equal to this part. Why? Because beta is a constant. So I don't care about this beta anymore. So I directly equal to that. Okay. And now use the conclusion that we just proved. That should be what? That should be this part of A times the covariance and times that one, right? Okay. So it should be this one times covariance of epsilon and times this one T. Right? And continue. What is the covariance of epsilon? See here? Epsilon for each one, they're independent, and each one is what? Is epsilon squared. So the covariance matrix of epsilon must be what? Must be a diagonal matrix with epsilon sigma square, sigma square, sigma square, right? Let's say this. Clearly, the covariance of epsilon this equal to this. Oh, Jesus. Sigma square. Okay, so this one should be this. Why? Because of this. Covariance is 0, independent, so all others are 0, and all of them are sigma square, right? So this equal to sigma square times I, okay? Where I is the identity matrix. What's the dimension of this? Let me see. N, yeah, that should be N, because sigma, I have total M data. So this equal to what? This simply equals to sigma square of this. Come on, get out. Sigma. Okay, now you can easily calculate the answer. Why? Everybody knows how to calculate this one. Do I need to write it down? The t is, this gives you an x here, an x here, and then gives you an x inverse here. That's it. Come on. How can I delete that part? That's so stupid. Okay, good. That's why I really don't like what word. Okay, now see the point? This part gonna be deleted. Gonna be canceled. Why? Because they have this xtx, and this is xtx inverse. They're gonna cancel, right? And here you have this. By the way, xtx inverse is it's what? It's a symmetric matrix. Okay, that's why after t it's still itself. You know what I mean? This is nothing but a b t equals to bt at. That's it. Okay, so that after inverse you're gonna have xtt, which is x here, become here, and then xtx inverse have a t because it's a simple symmetric, so that it's itself. So this finally equal to this sigma square, and then copy and paste this part and done. Okay, that's how you can prove this conclusion. Clear? Any questions? This is very simple, right? Okay, now any questions here? No question. Okay, now let's have a look at something else. So in this case, we have proved that the beta is in this distribution. Okay, in other words, this tells you that the OLS solution, the least square estimator of beta hat, is an unbiased estimator of beta, the true parameter beta. Okay, this is the first thing. The second thing, important thing, is how does the sum of square, the residual RS sum of square distribute, and how to estimate this sigma square. Usually people may say, oh, simple, sigma square, right? 1 over n minus 1, and then, you know, the sample variance. Unfortunately, it's wrong. It's biased. The real unbiased one is here. And let's see how to get this result. By the way, these results are not that easy. For example, if you check the ELS, the element of statistical learning, nothing there. I proved it by myself. Okay. So if you wanna take some notes or something, you're welcome to do so. Here I had a lot of things like did it by myself actually. Okay. Where it is? Here we go. So to make my life easier, I define the epsilon hat, which is the residual, you know, equal to 1 minus y hat. Okay, now the RSS, which is the residual sum of squares, is nothing but this, right? I guess most of you, all of you, I think, should already have learned a little bit about the linear regression before, right? So I think you are familiar with the notation like RSS, this kind of notations, right? Okay, so I'm not going to introduce more about RSS. Here I'm using everything, use matrix operations. I know many of you might have learned something from some courses. They give you some easy things like RSS equal to, I forgot the formula. Like there are a lot of SS. This SS1 and SS2 or something. These are very simple. All of these are called what's the name? Simple or single kind of like linear regression things. These are too simple. These are very, very special cases of my operations here. Here is a very, very generalized all matrix operations. And the one you learned like algebraically, like calculated by the calculator or something, these are special cases. Okay, now let's have a look. Because I have sigma hat equal to this, and then I substitute that my y hat equal to x times b hat. So that I just plug in, and your beta hat, your beta hat is this times y, you know it. So that you plug in, it's going to be this. Now I define this one, this part to be Q. This part is defined to be the Q matrix, okay? And by some analysis, you're going to see its dimension is n by n. So that this one simply equal to Q times x beta plus c. This is because of y equal to x beta plus c. And the very interesting thing is that q times x times beta is 0. To see why, you just need to do some very basic operations. Come on. Oh my goodness, why the computer is so slow? Now I think I can take off the fan. Okay, so your qx beta equals to what? Equals to, no, I even cannot copy and paste. That's something really bad. IM minus x t x inverse x t, and this one times x beta, right? First of all this can be canceled, and this times, actually it's already there. That's so simple, Jake. And this equal to x beta minus x beta. Equal to 0. Okay. Any questions about it here? Any questions here? No? Okay. So if qx beta equal to 0, so this item simply equals to, yes?
No question.
No question? Okay. So this item simply equals to q epsilon. Okay. Now let's have a look. If this one is q epsilon, what's going to happen? Another very important observation. To be honest, this is a trick. It's not easy to find it. But you know, researchers, they tried this decades, many decades, and some smart person found it that q squared actually equal to 0. Why? You are just gonna, you know, do the operations, the verification, simple verification. You're gonna get it. Q squared equal to this times this, and then you can easily verify it. Equals to 0. I'm not gonna do the details. This is I, and this and this, they cancel each other. You're gonna find what? You're gonna find another I, yes. And this is gonna find you another I. And if you put these two parts together, no. I think there's a two item. Yes, there's a 2 item here, because this gonna cancel. That's gonna be x times xt x inverse t. And then here you're gonna have a xt minus 2 times of here. Then finally you're gonna get 1 time of here, and this is also 1 time here. Then plus and minus cancel each other. Then you're gonna have an in as well. Yes, so that you're gonna have in minus in, which equal to 0 finally. Okay, so if you have this, that tells you what? Q squared minus 2 equal to 0. It's a super important thing, Cayley-Hamilton theorem. I don't know whether if you've heard of this. This tells you that if your polynomial of the matrix follows something like this way, then you plug in your eigenvalue, it's going to have the same form. Have you learned about this one in linear algebra? And this is also the method. How can we find the polynomial of a matrix? By the det lambda x minus I. So det minus I minus det a minus lambda I, and you get the det equal to 0. Then the solution must be the eigenvalue. This is also because of this. Okay, we can actually Google it. Let's see. Kelly, and you're gonna see a lot of such. You're gonna see a lot of such trick that I first find a polynomial of the matrix, and they take advantage of this matrix, the root directly as my what is my eigenvalues. Once I have eigenvalue, I can take advantage of eigenvalue to many things, especially if this Q is a full rank, I can diagonalize it, and then many of my analysis is gonna be based on my diagonalized the eigenvalue vector. Eigenvalue the matrix. Then everything is gonna be much easier. So this tells you this. For example, suppose you have something like this way, it's equal to 0. Then this is gonna also be what? Also be your eigenvalues. And using this way, you can also construct a matrix such that the sum of eigenvalues equal to the trace. Okay, all of them are actually by this Cayley-Hamilton theorem, which is very, very, very important. I would say it is the most important in about eigenvalue theories. Okay, now if you have this one, you immediately have what? You immediately have lambda square minus lambda equal to 0. In other words, your lambda must be either 0 or or 1. Then the question is, you totally have n lambdas. Question is, how many are 1? How many are 0? You don't know it. Okay, now we're going to take advantage of what? Take advantage that the sum of lambdas equals to the trace. Have you learned about this theory? You know what I'm talking about?
Yes.
You and I have a question here.
Yes.
According to your note, q squared is q, it's not 0. And then q squared minus q is 0.
Yeah, of course. Yes, correct. Q squared minus q equal to 0. Yes. So we have lambda squared minus lambda equal to 0.
In the Word file, you said q squared is 0.
My fault. Sorry. H should be equal to q. You're correct. Yes, H should be equal to q. Okay. Let me do it. Let me do it. I try to be lazy, but looks it doesn't work. Minus 2 times. Thank you for finding it. I even didn't realize it. And plus what? Plus let me see. This cancel plus itself. Right? And then you're gonna have what? IN minus this item. And that's the definition of Q. So that you have Q squared equal to 2. See it? 2Q. See it? So this theorem tells you what I'm talking about is, suppose A is in, doesn't work. Let me find an R here. Where's R? Let's say n by n. Then sum of lambdas is equal to the trace of A. Okay, I'm talking about this. So using this thing, if I want to see how many lambdas are 1, I just need to have a look at the trace of Q. Because Q equals to I minus this, right? So the trace of them, of course, you take the trace both sides. So you're going to have this. Okay, now very clear. Can I enable scrolling? Okay. So now very clear. The thing is what? The thing is the trace of IN, of course, that equals to n, right? Okay, now you want to have a look at the trace of this. And do you know this theorem, this property? Very simple. Trace of AB equals to trace of BA. Correct. By the way, do you know what does trace mean? Yes. I assume you know what does trace mean, okay? Arab and Said, do you know what is trace?
Yep.
Okay, the sum of diagonal elements of a matrix, okay? So this is very simple. You can easily verify it. And by the way, you'd better know this. Another interesting thing, theorems here. Actually, for Arab, you should have known it because I showed it in IME 470. A dot B, inner product of B, this equal to what? This equal to the trace of A, BT. And also equals, of course, the trace of ATB. Okay? This is something else for the trace. Okay, if I have trace AB equal to trace BA, that tells you what? That tells you that trace of ABC equal to what? Equal to trace of, from BCA, right? And I can just use this order to permutate it whatever I want. For example, this also equal to CAB. And you can permutate it one more time, which is AB. Oh, okay, well now I'm done. You know what I mean? You just use this A, B, C, and then put A back, then BCA, and then put B back, CBA, then put C back, ABC. You see it? And you can do it for 4, 5, 6, whatever you like. So here we use the trick in this way. So if this is A, this is B, this is C, so trace of this equal to put this one back here, the trace of this part. And these two cancel. And be careful about the dimensions, okay? Your X dimension is n by p plus 1. So that this I is IP plus 1, meaning that an identity matrix with p plus 1 dimensions. So totally, your trace of Q equals to n minus p minus 1. Okay, now you see what happened is the eigenvalues, all of them must be either 0 or 1. And the sum of them must be n minus p minus 1. That tells you what? There's only one possibility that I must have exactly n minus p minus 1 ones, and all others are 0. Right? This is the only possibility. Okay, now for that case, let's do the eigenvalue decomposition. And you, excuse me, and you're gonna see, let me take some water, sorry. And now we're gonna do the eigenvalue decomposition in this way. Why do I need to care about how many ones and how many zeros in the eigenvalue? Because I need to know the structure of this nebula. This, lambda, this lambda matrix. This lambda matrix, I know that it must be in this form where I have exactly n minus p minus 1 diagonal elements being 1. This is extremely important. Why? Here, in the norm operations, you're going to immediately capture the most important information. Let's continue, and you're going to see it. Okay, now let's have a look at RSS, sum of residuals. As we define here, sum of residuals equal to, equal to the sum of residuals. And sigma hat is the residual, so that it equals the norm of the sigma hat. Okay, square. And then you plug in. Sigma hat equal to what? From here, 14c, sigma hat equals to, not sigma, sorry, epsilon hat. Epsilon hat equals to Q epsilon, right? So Q equal to what? Q equal to V lambda VT. Okay, so we just plug in. So sigma hat, epsilon hat equal to Q, epsilon equal to V lambda VT epsilon. Now, because V is a unitary matrix, unitary matrix means orthonormal or orthogonal matrix, okay? Unitary matrix, or you can call it orthogonal matrix, or you can call it orthonormal. To be honest, a formal way should call it unitary or orthogonal, because orthonormal is kind of a language for vectors. But my personal habit is that I would prefer to call it unitary or orthonormal, because orthogonal, it's not that clear that it must be the unit, the vectors must be unit vector, meaning that it must be, all the vectors must have norm 0, norm 1. So if a matrix, let's say a matrix V is unitary, that tells you that VT equal to V inverse, which is equivalent to say that VT equal to I. Okay, so this is the definition of orthogonal matrix, the unitary matrix or orthogonal matrix. And but what's the point? The point is that suppose in the norm I have such unitary matrix, I can ignore it. Why? Think about this. Consider Vx, the norm. Okay, this equal to what? This equals to too ugly. I cannot tolerate it anymore. I like the things to be very organized and be professional. I mean, in writing, unfortunately, my desk in my office or at my home is never that organized. Okay, so Vx, so x is a norm, right? This, I want to tell you that Vx equal to x, where V is a unitary matrix. This equal to what? By definition, this is Vx T Vx. Right? This is my definition. Okay, this tells you what? This tells you xt Vt Vx. And this tells you xt x. Why? Because of this. VTX equal to VT equal to I. That's it. Okay, so that they cancel, and this equal to what? This equals to the norm of X. So that as long as you see there's a unitary matrix inside, you can just ignore it. So go back here. V is a unitary matrix. Why? Because V is from eigenvalue decomposition. So that I can cancel this V. You cannot cancel this V, be careful. What I'm talking about is the V in the beginning or in the end, okay? So you can cancel this V, and this equal to lambda, VT, and epsilon, okay? And now, to make my life easy, I define this item. VT epsilon is what? Is a vector. Be careful here. Epsilon is something random, okay? It has some randomness that you don't know what is epsilon. Now I'll let you defined to be VT epsilon. And now this, I should have how many U's? The dimension of this U should be n dimensions. Why? Simply because Q is n by n. Okay, now you can rewrite the RSS to be what? To be lambda U, the norm of this. Again, lambda U gives you a vector, okay? And now lambda U equal to what? Equal to the UI uj square summation. And be very careful, it is not a j from 1 to n, but a j from 1 to n minus p minus 1. Why? Because of your lambda matrix. Your lambda matrix is defined in this way. See it? You only have n, the first n minus p minus 1 diagonal elements to be 1, and all other diagonal elements and all other non-diagonal elements are 0. Okay, and that's the reason why the norm of U actually is only the norm of the first n minus p minus 1 items. And that's, if I have this way, that's something you're gonna immediately see. Why? Because first of all, by the definition of U is VT epsilon. And what is epsilon? Epsilon is in this. Right? Epsilon, the distribution is normal distribution with covariance matrix, which is nothing but all epsilon, all sigma square. So since my U equal to VT times epsilon, what is the distribution of this? See it here? We still have it, right? Where it is? It's here. We still have this conclusion. So your variance of where? Your variance of U must be what? Must be VT times the covariance of epsilon times V. The covariance matrix of epsilon is sigma square IN, so that your covariance of U must be sigma square VT V. And VT V cancel each other again because it is unitary. So your epsilon is this. Okay, now what is this, guys? This is a standard normal distribution except for the what? Except for the covariance or the variance, right? In other words, if I have a UI divided by UI, not U matrix, okay, UI is one random variable divided by sigma square, it is what? It is standard normal distribution. Okay, guys, what is the square of standard normal distribution? Chi-square distribution. How many you have? How many degrees I have? Okay, now you immediately get this, and this is super important. Your UI must be follow this way, right? So UI divided by sigma square must be a standard normal distribution. Substitute everything back. Your RSS is what? It's a summation of from U1 to UN minus P minus 1. Sum all of them and divide by sigma square. And then you're going to have this. And this must be a chi-square with N minus P minus 1 degrees of freedom. Get a point? Very important. In other words, hey, I need you to get the distribution of RSS if I know the sigma square. Extremely important this is. Okay, the question is you don't know sigma square. So I do need to estimate what sigma square is from my data, right? Okay, and again, we can take advantage of this. First of all, let me ask you, is this conclusion clear to you guys here? So far, I mean, this conclusion.
Yes.
Clear? Let me write down something. I wish I have a whiteboard. Everything's going to be much faster. If if let's say xi follows n 0 1 IID, okay, need to be IID. Then the sum of let's say k defined by the sum of I to let's say n I square this must follow the chi-square distribution with with the sum of the degree of freedom df equal to n. So similar here, uj square over sigma square follows normal standard normal distribution, and they're independent. Why? Because epsilons are independent, so these ui's must be independent. So that you have n minus p minus 1 ones of minus 1 this kind of sum of standard normal distributions. So your degrees of freedom as chi-square distribution with n minus p minus 1. And you know that the mean of chi-square distribution is equal to its degrees of freedom. Okay, let's search something here. That's gonna be easier. Chi-square distribution. Okay, so let's have a look. Okay, so you don't need to care what the PDF is. I never remember the PDF of chi-square distribution. I just remember it's difficult. And the median, the mean is here. Mean is k. See it? With degrees of k. So the expectation or the mean of it is k. So here, have a look. My degree of freedom is n minus p minus 1. So my mean or my expectation must be n minus p minus 1. So that I have expectation of this equal to n minus p minus 1. And I change the things to be this way so that I have RSS divided by n minus p minus 1 as sigma square. Now you see what? An unbiased estimator. You remember what is unbiased estimator? That is the expectation of my estimator equals to itself. So if I set this one to be sigma hat, square hat, so it equals to itself. That's why it must be what? An unbiased estimator. See it? Okay, now RSS you can easily calculate, right? What is RSS? RSS is nothing but yi minus yi hat. What is y hat? Y hat is nothing but x beta hat. Beta hat is what? Is nothing but this. Okay, so that you have what? You simply have, okay, let me write it a little bit here. Sigma square defined to be n minus p minus 1 of RSS equals to what? It's raining outside. Really? Minus p minus 1, and here should be let me see. Y minus x okay. This must be an unbiased estimator of sigma square. So in this case, all the statistical inferences of this linear regression model has been made. Clear? There are a lot of online methods using some other things, you know, because I searched it, use this kind of like sum of squares and sigma this, sigma that. Oh my God, make it a really kind of like headache, because there are so many items, and all of these are special cases of this. As long as you know this proof, you solve everything. That's it. Everything is by the matrix operations, okay? Please read the proof clearly and do it step by step after this class, okay? So here it does use the trick of the unitary matrix, but to be honest, this step is very, very difficult to be found, this one. As long as you get this one, I think all others are very normal. I think everybody can get it. But this one's difficult. I mean, you have to admit there are some people very, very smart and have very, very good observations who got this one. After getting this one, everything's gonna be simple. And by the way, Mahabuba, remember last year in the research, we take advantage of this one, and we added a weight parameter, which works as a permutation matrix. Remember it?
Yes.
And you're gonna have something not exactly the same, but very, very similar, because you also defined this one in this way. Remember it? Actually, somewhat this proof, I referred it from that book, the matrix. What's the name of the book? By Gloves, Matrix Computations. Yes, that's how I refer to that book. That's how I proved this. I don't know whether any textbooks have this proof or not. I got this proof by myself. But to be honest, this step I stealed from some papers. This is not my original idea. All others are, very, very standard and very, very simple. Okay. Any questions about this one? No?
So I have a question here.
Yes.
You just talked about that this interesting property that q square minus q is 0. And then you conclude that this polynomial shows that all eigenvalues of q must be either 0 or 1.
Yeah. Why?
Yeah, why?
This Clay-Hamilton theory.
Oh, it's based on that theory?
Q square, Q is a matrix, right? Minus Q equal to 0, right?
Yep.
Okay. This tells you, let me make it bold, because this tells you that they are indeed matrix. Q square means QQ, okay? Because Q is a square, square matrix, so I can do Q square. This tells you that lambda square minus lambda equal to 0. That's the power of Clay-Hamilton theory.
Okay.
You know what I mean? Any polynomial that you have. Okay, so in general, it's in this case. Suppose you have the root, you have a polynomial of q. PQ equal to 0. Be careful. This q is a matrix, okay? Matrix. But this tells you that if you have this, then you must have p lambda equal to 0. And this 0 and the lambda, they are scalars. They are small, numbers. That's how powerful it is. I forgot the proof, but I remember the proof is not that easy. It has a lot of steps, and that proof was my nightmare in my undergrad, because I remember I had 2 exams related with this, not the whole proof, but I used the ideas of the proof, and I got wrong in both of these 2 proofs. That became my nightmare. But unfortunately, because I made the mistakes twice in my exams, so that made me very difficult to forget this theorem. At least I remember the theorem, although I forgot the proof again. You're free to see the proof. The proof, I don't know whether it's showed here or not. Let's see. This is the great guy, Kelly. And Hamilton, I guess many of you know, a very, very famous mathematician in algebraic. Does it show the proof here? A direct algebraic proof. Really so short. The proof that I saw, I remember, was longer. I forgot the details. Anyway, if you are interested, you can search it, but this is not a point. Okay. Any questions about?
Okay, I have another question.
Yes.
So in eigenvalue decomposition, the VT and the V are orthonormal.
Yeah.
So what about single value decomposition?
Single value decomposition, you're also gonna get unitary matrix, but the difference is that you're gonna Q equal to U lambda V rather than V lambda V. You know what I mean? That's the reason why I said eigenvalue decomposition is a special case of single value decomposition, in which your V equal to U. It's a very special case. Be careful, eigenvalue decomposition. Not every matrix has an eigenvalue decomposition.
So in single value decomposition, are U and V orthogonal?
Yes. U is orthogonal, and V is also orthogonal. That means UTU equals to I and the VTV equals to I.
Equals to I.
Yeah,
Okay.
but the U is not necessarily equal to V. If and only if the matrix has eigenvalue decomposition, then yes, you can do it. You can claim that U equal to V. But it's really, really important.
Okay, thank you.
Yeah, you're welcome. Any other questions?
No.
No? Oh, we're a bit too slow today. Let me introduce a little bit. At least let me finish this Z-score or T-score. Let me see. We have a little bit about hypothesis because to my plan I should have finished this part. Anyway, so we have something about hypothesis testing. This is very applied because in the real cases, if the data is really low dimensional, it's easy for you to, for example, draw it. But if it's a high dimensional, it's difficult for you to draw it. So usually the method is this. Suppose, for example, I have 5 dimensions. What I'm going to do is that I'm going to choose 2 of them. You know, 5 choose 2 equals to 10. So you're gonna draw 10 groups of the data, and then you're gonna see whether in most of them the coordinate system they are linear. If most of them are linear, you're gonna use the linear regression. If most of them are nonlinear, then probably you're not gonna use the linear regression. This is still low dimension. What if, say, I have 100 dimensions? 100 dimensions, if you want to draw the pictures, so how many cases you're going to have? You're going to have 100 choose 2, which equal to 4950. So you need to draw 4950 pictures, and you want to look at it, all of them by your eyes? Probably not, right? So the hypothesis testing method directly shows you the way that no matter how many dimensions, you can directly do it. So first of all, I want to see whether a beta j is significant. A single beta j is significant. If it is significant, that means, yes, I need to keep this beta j in my regression model. If it's not significant, kick it out. Very simple. Remember in the logistic regression, I think, where I introduced a z-score there, exactly the same meaning, actually. I think it's a logistic regression. Let me open it. It's here. Logistic regression, and let's view 2 pages. Here we go. So here you can see I do have the z-score. See here? This part. They're actually the same, okay? But the difference here is that suppose I don't know this sigma. I use sigma hat to estimate this sigma. Then in this case, the z-score is going to be t-score. You have all learned basic statistics. You know that what's the difference between t statistics and the z statistics? When they are equal, at what time they are equal?
When we have the sigma or sigma square, it's going to be z. But when we estimate it, so it's going to be t.
Right. T is a student distribution, right? When your number of data, the parameters, the Tn, the n is large. I think as long as it's larger than 30 or 40 around, something like this.
30,
you can use, you can use the
sample size is bigger than 30, yep.
Then T and the Z gonna be very, very close. But theoretically, we still put the T here. Although in the real applications, there are no difference because in most cases, you must have more than 30 data, so they're almost the same. So you're gonna do the hypothesis testing, very clear. And all here are very basic, this kind of hypothesis or confidence intervals for the T statistics or for the Z statistics, okay? So here you have the, in the T distribution, you have the data of degrees of freedom as n minus p minus 1. Why n minus p minus 1? Again, because you have degrees of freedom in the linear model that you have n equations and you want to solve p plus 1 coefficients. Again, here, we all assume n is greater than or equals to p plus 1. In most cases, we have n is greater than p plus 1, okay? And so here, I will suppose I want to reject h0. I should have what? I should have something very large, right? Let me draw it here. Let me draw a line here, and then the curve I have to draw by my hand. Don't laugh at me. I'm not good at drawing. Oh, good, not too bad. Something like this, right? And then I'm gonna have the 2 percentile numbers here. And your acceptance region. This name is not formal. The formal way is the rejection you will the region you will not reject is in this part. In other words, if your t is here or here, then you're going to reject it. That's the reason why a large t is going to absolute value. A large t will cause the rejection. Okay, rejection is a good point. Why? Because rejection tells you that the beta j is significant. You reject null hypothesis, which is beta j 0. Okay, so in other words, suppose you have an absolute value of t as relatively big, then you're going to keep this beta j. If it's small, you're going to remove this beta j, this single coefficient. Okay, and similar when n minus p minus 1 is large, so we're not going to use t distribution anymore. We're going to use the standard normal distribution so that your t statistics becomes the z statistics and everything exactly the same. Okay, regarding this part, I don't need to review, do I? This part, because this is nothing but very, very basic statistics. I just erased the figure. Let me see. Okay, here we go. For z, the same. You know, just something. T is a bit taller, z is a bit flatter. That that's it. And a big one's gonna be there, and the confidence interval of 1 minus alpha over 2 is this confidence interval. Okay. In other words, if there's a number, the beta number something is inside it, the score here is inside it, then you're gonna accept it. You will not reject. In other words, yes, beta j should be kicked out. If it's outside, then beta j should be included. It's significant. Okay, so this is the hypothesis testing for a single beta j. In some cases, however, you want to do a group simultaneously. Why group simultaneously? You might say, oh, okay, so why don't I, for example, I just kick one by one, right? Why should I kick it simultaneously? First of all, remember, in the logistic regression, we didn't do it simultaneously. We did kick one by one. And remember, here's an algorithm where it is. Let me see, South Africa. That I'm going to take one and kick one, and then I'm going to redo the regression, kick one, redo the regression until all of them are significant, which is greater than or equal to let's say 2. Absolute value is greater than or equal to 2. Or you can say 1.92. Why? Because this is 97.5 percentile of the norm distribution, which is amounts to 95% of confidence interval, right? And until everything is significant, then I'm done. But here, in some cases, you want to kick out several beta j's simultaneously. Why? Consider about this. What if beta j, a group of beta j indicates a category? Suppose you have, let's say, for example, suppose you are thinking, let's say, whether the income is related with your degree. So your category of the degree, for example, high school, undergrad, PhD, for example. So you have 3 category coefficients, right? And then you may want to use beta 1, beta 2, and beta 3 to indicate which one. And then, of course, you're going to have x1, x2, x3, the sum of them equals to 1. That means that you exactly have, everybody must exactly in one of them. The question is, maybe the degree itself is not related with your income at all. Maybe. In other words, this beta 1, 2, 3, they should be either included together or removed together, right? It doesn't make any sense. You say, oh, I just want to remove the high school. I want to keep the undergrad. So how about these people whose degree is less than or equal to high school, right? So in this case, yes, you want to consider all these category coefficients of one group together. You're going to either include beta 1, 2, 3 together, or you're going to remove all of them together. So in this case, I want to do the hypothesis testing for a group of betas simultaneously. Okay? Then we need to use the F distribution. Due to time limit, I don't have time. I'm going to introduce it in the next class. By the way, next Monday is the Easter's Day. Somebody reminded me, I didn't know it as well. So we do not have class next Monday. We will continue the class next Wednesday. Okay? Now, I think that's all about today's class. Thank you very much, and I'll see you next Wednesday. Goodbye. And Mahbooba, don't forget our meeting. I will be back in about 5 minutes. Okay?
Yes.
Okay.
Thank
Bye.
you. Bye.
Thank you.
Bye.
Bye.